Without further ado, let's get started. The first speaker today is Ram Rajagopal from Stanford University. So Ram, the floor is yours.
Thank you, Alejandro. I'm just sharing my slides here. So hopefully everyone is able to see them. So today I just wanted to talk about some work that we have been doing for the past couple of years on really mapping all of this new energy infrastructure that's being built. And I want to address, why do we do that? And what are some of the insights we can gain from this exercise? So the global renewable generation penetration is increasing dramatically. And you can see here on the left-hand side picture, that the demand is also growing because it's expected to grow because of electrification, of transportation, and the consumption of other sources of energy. And then a substantial portion of this new demand is going to be met by solar, wind, and so on. And in fact, in this Bloomberg 2020 New Energy Outlook, solar and wind will account for 56% of the installed capacity in 2050. You can see right there. And distributed solar and storage, which are, the large components of distributed energy resources, are expected to account for 13%. So that's not shown in the figure. What does that mean, kind of in summary, just some numbers so you get, the order of magnitude of the amount of infrastructure that's expected to be built. In global solar and wind energy, we are expected to produce from 2,300 terawatts today to 45,000 terawatt hours by 2050. If you look at stationary storage penetration, it's expected to reach 4,500 gigawatt hours of energy capacity by 2050. And right now, 95% of it is pumped hydro, but by 2050, we are expecting 50% of it to be lithium-ion batteries. And DRs represent a very large and rapidly growing energy resource, with distributed solar and storage expected to reach 3,000 terawatt hours by 2050. EVs consuming 1,290 terawatt hours of energy by 2040, with an expected 300 million charging points in the grid. And then in addition to that, we have flexible loads in the orders of hundreds of terawatt hours. But by the way, the statistics on that is even lacking in most of the studies that I've read and seen. So now we are heading to this place with a substantial change. And one of the things that is kind of important to do for the grid is to kind of measure the impacts. So how do we measure impacts? What are things that we are worried about? There's many things, but I wanted to highlight three of them. The first one is, what are the adoption patterns and what are the key drivers? Where is this infrastructure being built? Obviously, when you think about distributed energy resources, there's an element there of consumers making decisions, and it makes a lot of sense to talk about adoption patterns. But even when you look at transmission level deployments of utility scale technologies, there is a question of how the incentives were laid out, what is the way the markets work, and where are these technologies actually happening, and what is the overall impact of that. In order to do that, we need data on when, where, and what was the capacity of these new technologies that were deployed. A second thing that I think is kind of becoming important is to understand the exposure of this system to extreme events. So this has been, of course, in the media because of what happened in Texas this year, and the really bad summer we had in the West Coast last year. But generally, this is an important question. And when you're looking at extreme events, you in addition to the supply and demand information, you definitely need to know about the power network interconnection. And I think a third thing that is going to be very, very important as we move into the future is actually quantifying the impact of these technologies on the grid. So there was a lot of early work on that, from 2008 and so on. But I think with the higher amount of deployed technologies, there's a lot more we can do. For that, we need data on actual generation, consumption, network parameters, and so on. So in this talk, I really want to talk about the first two problems, both of which require mapping of the data. So when, where, what's the capacity of new technologies, and what's the power network, and what's its interconnection. So, for conventional power, there's a lot of geospatial databases out there. In this slide here, I'll share my slides later on with the organizers. But you can see, there is a mix of different types of databases. Some databases are built by researchers and activists, like the one in the top left corner here. There's databases built by national labs who actually have specialists who use various techniques to actually go and make sure that all of these plans that are mapped are correct. There's databases that use crowdsourcing or even voluntary contribution of information. But when you look at this for renewables and DERs, the situation is a little different. First of all, we don't right now know their exact locations and their capacities. There are projects out there that you can go and download data. So one example is for the Open PV project. But when you look through the type of data that's made available, it's mostly voluntary contributions. Sometimes they obtain, and I'll show some examples later, documents from the state and try to garner this information. And typically, they are incomplete. They lack the exact GPS location, and this is not an issue just in the United States. Even in Germany, they have, for example, a PV registry, and it lacks exact GPS locations. They're hard to update. A lot of these projects consume millions of dollars to keep up to date, and then they are quite behind in terms of the mapping. And they contain lots of duplicates of information. There was a nice report that was issued last year by the EIA, and it said, well, we only know where 50% of the wind turbines and 40% of the solar systems are globally today. Now, how about the power network? So the situation there is a little different, because there is, first of all, the transmission grid connectivity is very well documented. And at some level, there's publicly available information about it. So some aggregate models that would allow for studies to be done, or even, thoughts on capacity expansion and things like that. But when you look at the distribution grid, there is very little out there. There's some utilities who have shared, simplified models of their networks. But in general, what we find is it's typically outdated, inaccurate, and even unavailable in the US, and it's the situation can be even more critical in places like Africa and so on. So what is our proposal? Our proposal is to kind of build this atlas that maps all of these resources. And we wanted to make sure that the data that is used is open, so that anybody could try to replicate this mapping effort in whatever location they are. We want the results to have temporal and spatial granularity, and I will discuss why. I'll show some examples of what conclusions you can reach with this. And we want to share the data as well as all the code that generates all of this data with researchers, policymakers, and so on. I think this is a very important step, as right now, for example, we are trying to determine what are the optimal investment strategies for enabling a more equitable build out of the grid, as well as what investments would help with climate adaptation. And to do these studies, you need some data as a starting point. So what's our framework? It's a fairly kind of simple idea, but it grew organically, and now we're able to do a lot of things with it. But basically, you can take open data sets. We started with satellite imagery, but right now we work with satellite imagery. We work of different resolutions, so we collaborate with folks looking at the lower resolution imagery from Landsat and so on, as well as high resolution imagery. We use Google Street View imagery. We use road, the open street maps. We are using building permits. There's a lot of data sets out there. And as we have been working with this, we are contacted constantly for the data that we produce. And as we share, we also discover that people have excellent suggestions about what else can you do. And the idea is to use this data and just apply, appropriate machine learning algorithms to kind of detect the infrastructure of interest. Now, a lot of times we start with very well accepted methods, and you might need some fine tuning. But in some situations, we have had to combine various methods. For example, in the network case, because you have several issues to solve. And once you have these detections, you can build different layers of the map for the different infrastructure, and start to do all kinds of analysis and correlations. So that's kind of the basic framework that we developed. I already talked a little bit about the type of data that we are using. And here on the right-hand side, you can imagine what are all the things that you would like to have in this atlas. On the supply side of the game, we want to have all the solar installations, residential, commercial, utility scale. We want to have all the wind installations, conventional power plants, which, as I showed you, we already have a lot available. On the transmission side, we want to have distribution grids. But also, if you have an interest in understanding resiliency, you have to start to map, the gas pipelines and interconnects, and so on and so forth. On the demand side, I listed here, EV charging. That's one area that I think is very important, and you want to be able to model that. And you have, meteorological and environmental variables. Highlighted in red are some of the mappings that I'm going to talk about today. But here at Stanford, as part of this initiative, there is a group now that decided to, work on the mapping oil and gas infrastructure as well. And there's another group that is starting to map all the hydropower dams in the United States and try to provide estimates of kind of water height to understand, the effects of climate change. So it's quite exciting. So we started, in 2017 and actually 2018, we published this paper, Deep Solar, which was mapping solar panels across the whole country. And it was built after a couple, two of my students went to, a meeting with PG&E and they told us, well, we don't know where the solar panels are in our system, which is kind of surprising given that, they have net metering and all of that. So what is the system? Well, we use CNNs to classify the presence or absence of solar panels. So we built up on top of Inception to do this, which is kind of a standard computer vision classifier. And then we utilize this idea that if you look through this network, in some of the layers, it will highlight the most likely location of solar panel pixels on an image. Because for the training of this, we didn't want to have to outline every panel. It would have been very painful to create a good enough training data set. So we took photos, like, these are smaller blocks here of the image. And we just say whether there is a panel in this image or not. So there's panels in all of these, except this one here. But there's also other stuff that is not panels. So, but the machine learning method is able to learn that. And then you can go and look at this class activation map layer, and basically it will reveal the segmentation of the panel itself, and you can stitch everything together and kind of get your estimate of the solar system. So the classification rates are really good. You can see here, the precisions are high and a very high recall. There's a lot of optimization that was done for the algorithms to run fast enough so that you can run it on about 2 billion images, so that we could map the United States. We also did an exercise with Germany, so collaborating with folks over there. And then on the size estimation, what we found is at the individual panel levels, errors were large. But if you aggregated it and asked, what is the average size or total size of solar panels in the census tract, we had a pretty good estimate on low error. Now, this data set is available on deepsolar.stanford.edu. We are updating it later this year as part of a new effort that we're starting here with Precourt. And it provides, solar panel deployment density at the census block level. The results have been reproduced by others, and they even tried retraining and things like that. And we uncovered at that time about 20% more panels than the Tracking the Sun initiative plus the NREL database. And we have been in conversations with them about, how they can use this. They want to use this information to update their databases as well. So this was really interesting, but we were not sure, does the method work, outside of the US? And we partnered with Ben and Kevin in Germany to develop a model of deep solar for Germany. And the difference there is that we also had 3D building data available, which allows you to know the orientation of the rooftop and the tilt. And you can combine that information to get much better area estimates. So you can see there that now, we have a model that you can get, capacity estimates for each panel in the system with errors of 16%. This work is ongoing. There is some partners that are developing these models for France and other countries. And we are super supportive of anyone who wants to enhance this database. So why is such data useful? So that is like the million-dollar question here. Why do all this effort? So here I'm just doing some trend plots of what you see in the US. We take the number of solar systems per 1,000 households in the different census tracts, and we plot it against different quantities. So it's just the simple statistics, and these dotted lines that you're seeing are just trend lines. The first observation is that if you plot it against solar radiation, you do expect more panels or systems where there is more radiation. But we notice an interesting phenomenon here where, when the radiation hits 4.5 kilowatt hours per meter square per day, there is like this triggering of adoption. Adoption increases with population density, but at some point it starts to decrease. Again, this kind of makes sense because, as the density becomes higher, you have apartment buildings, so the population density increases, but the rooftop area does not increase. In the paper, we do analysis with rooftop area as well, which is not kind of shown here. It didn't make much of a difference in terms of the trends that you would see. If you look at income, again, we see increasing adoption with income, but there is a saturation. And then, there is a lot of results that argue, there's some type of inequity in the adoption of solar. And you can see here, when the census tracts have a high Gini index, there's less adoption of solar. So more kind of inequality in a neighborhood means less adoption. So these are kind of interesting observations, but one key fact here is that we noticed all of these trends were non-linear. And, typically people have built adoption models that are linear. So, you could easily get better models if you accepted the nonlinearity, but, we are observing that because of the amount of data that we have. So what we did is to kind of showcase this. We built our own adoption model. And the interesting fact here about this adoption model, I would say, is that we created a two-level model. So there is a first model that determines whether a household will have a solar panel or not, will adopt or not. That's kind of that threshold idea. There is like a activation threshold for that. And then, in the second level of the model, we determine, in a particular census tract, how many systems will there be. And it does a reasonably good job. The out of sample R square is 0.72. If you look out there in the literature, we have like a long list here. At the time, the highest was 0.71, but this was in sample. So you can, guess that it's, out of sample is going to be less than that. Particularly because there aren't a lot of data points and there were a lot of features that were used in the regression. The most predictive features are what you expect. But one whole story here that we were not super happy is this kind of static, because we only had the detection without capturing the temporal change. So we decided to say, why not map the temporal change? How to do that? We can use the historical satellite images, as you can see here, in 2017, 16, etc. But what's the challenge in doing that? These images are older images, can be low resolution. And sometimes even in the newer images, the quality of the capture for a particular year may not be very good, because these depend on, when the satellite provider, is kind of driving over a certain area. Maybe there's clouds, maybe there's some other issue. And the other one is, object displacement, so you can see, the panel might move inside the box there. So we built kind of a comparison-based CNN model. So it's two inputs and it compares them, and basically it compares each one of the other year's image to the 2017 image, and it will output a positive or a negative, because we know that the panel has to exist on 2017. So then I can just track back to see when it doesn't exist anymore. Okay. So this work is not published yet. It's a preprint here, so you can contact me if you wanted to see the results. So so far, we have been able to generate a time series of system level data in 390 counties from 46 states. We are just obtaining the rest of the satellite imagery to complete this for the whole US. Just as a comparison, the LBNL, tracking the sun data set covers only 29 states and only at the zip code level. And you can see here, we have different places in California, and you can see that the onset of when the deployments start to intensify happens in different years in these different places. So one of the things that we were able to do with this data set is to start to look at what is happening to that adoption disparity that we saw before. On the left-hand side, we have a very simple plot. I wanted to ask, well, what is the cumulative share of all the new PV installations on that year over the different census tract or census block groups? So if the adoption was happening evenly over all the block groups, 40% of the block groups would acquire 40% of the new installations. And we can see clearly that's not the case. A very small percentage of the block groups acquire most of the adoption, but year over year, it seems to be improving. And that's kind of what you would like to have. Then we ask ourselves, well, is that improvement happening at every income level? Is that means everybody's acquiring more, or is that acceleration of adoption concentrating on a particular, income level? So how is that acceleration happening? Because in the beginning, we saw very wealthy people acquire the panels, and you can see that in data. And then over time, what's going on? So we calculated a very simple measure, which is just what was the speed up? So how many panels were adopted, on 2 date ranges, 2007 to 2011, and then 2012 to 2016. And then took the ratio of that, and we call that the speed up. And you can see there that like the speed up is mostly, on this range of individuals earning between 90K and 125,000. So the very rich folks adopted very early on, and now it's kind of still the wealthy, but not much speed up. And in fact, there's actually somewhat of a slowdown at the low income groups. So right now we started working with colleagues in the econ department to study, which policies, because we have such a rich data set, you can try to actually estimate the individual impact of different incentives from this data set. So we'll have more to report on that. We also looked at this issue of the solar diffusion. So this is a very popular topic in 2010 to 2012, where the idea was, well, if you see a few solar panels in your neighborhood, you are incentivized to put one yourself. And there was really this beautiful work by Graziano and Gillingham in 2015 that they found by looking at data in Connecticut, in a few of the counties there, that an extra PV installed within half a mile of where you are leads to a half of an extra PV, and then if it is within half a mile to 1 mile, it's a 0.4 of an extra PV. But because the existing studies only had the data for limited areas, they couldn't really look at the heterogeneity of this neighborhood effect. And what we were able to do is just go back to these models and ask ourselves, what is the impact of, this, what is the diffusion rates if we want to understand the impact of, the race of each census tract, as well as other considerations as well, socioeconomic considerations. And so you can just take a model. The model is kind of a simple regression model, where you have indicators for are there systems for each system that you have, are there systems, how many systems are there within a certain radius. So those are these ends here, and the radius are the 3 that I mentioned before, and basically follows what Gillingham did, but now we include additional socioeconomic covariates. And what we found is, first of all, that this neighborhood effect is really ubiquitous across the United States. It's significantly weaker in low-income communities. And then if you control for income level, we noticed that in Hispanic communities, it's stronger. So again, there is some policy understanding that can happen from here. And just to kind of conclude this part of on the supply side, we partnered with Professor Andrew Ng here and some of his students, and we are in the process of developing this model called deep wind. That's a wind turbine detection. The challenge there is, unlike solar panels, there's multiple wind turbines in a single image, and we also want to estimate the height and the blade sizes of all these turbines. So these are quite hard to do. We had an initial run around the nationwide data, and we noticed there's about 50% less turbines in the US wind turbine database than what we can find. But we're super excited also to we are working with colleagues in Brazil who want to build such a database there. So a very interesting project, more to come. The next topic here that I wanted to quickly go over is this idea. So we saw how to map supply. I wanted to figure out, can we also learn about the distribution grid? How do we do that? And the first observation is that, from satellite images, you can't see the distribution grid. The lines are too thin, and the poles, from the top, they don't really have a lot of volume. So it's very, very hard. And then, we started working with some undergrads in the summer from who were visiting the lab. And, our initial idea was, let's use street view images. And then from the side image, you can see some of these features, poles and so on. But the real click happened when a student realized that you can actually, in Google Street View, look upwards. So you can look to the sky, and if you do that, you can see all the lines. So that was the real click. And then, we can build a classifier to detect lines. We can then apply, what's called a Huff transformation. So it's able to detect, these, actually connect these lines, detect the actual lines on each image. And then we have a method that I will explain in a minute to localize all the poles. So we have there's a classifier for the pole detection, but then we can locate all the poles, and you bring these two pieces of information together, you start to have a map of the overhead network, and then you can post-process it to with another classifier to detect, what are the likely interconnects, because there will be some gaps on the map you're building. Just some details here, and I can share the paper on this one. But the interesting point is that the first interesting point in terms of the utility pole localization is that from the images, since you have multiple images, you can basically triangulate the location of a pole on the side of the street, which is pretty cool. So we did this for, we also had to build. So one of the things is, for example, here in the Bay Area, there is some fraction of the lines that are underground. And so how can you map those if you can't see? So our idea was, well, if there is a training data set, then we can take the map that we built overhead and then build a machine learning method that kind of predicts the underground lines. And how good can that be? So that's kind of what we have here. So first, on the side of the image level performance of detecting all, poles and lines and so on, there's a very high precision, pretty good recall. So performance is really good. And then the overall performance of kind of this prediction of the underground lines, it is also pretty good. And the trick is really that, we use data that's publicly available about the road network and the building maps. And it's not unexpected that, these lines are laid along roads. So this is pretty cool. We are in the process now of kind of taking, we took this model that we trained in the US and directly applied it to sub-Saharan Africa. So here are some of the some cities in Uganda, Kenya, and Nigeria that were suggested to us by a few folks who work out there, and they wanted this information. And you can see the results are fairly good, not as good in terms as they are in the US, but there was no retraining, no fine tuning. So there's a lot that can be done here. The next question we were asked last year was, well, you have all of this line information, and we are really worried about the exposure of these distribution lines to forest fires. So of course, we heard a lot about how these lines can ignite forest fires, but no matter if they ignited it or not, if there is a forest fire, you can actually, the poles can catch fire, and it can bring down power on those neighborhoods. So that's an actual real issue. So what we wanted to see was, well, can we understand, where we are at risk of this? Because there is a certain portion of the lines that are overhead, certain portion of the lines that are underground. So can we understand, are we having lines underground where the forest fire risks are, the wildfire risks are high? So we were able, so the first thing we did was to check in our model in DeepGrid, what is our quality in kind of predicting the undergrounding rate of these lines at the census block level. And you can see here the undergrounding rate is the amount of line length that's underground over the total line length of the distribution feeder on that census block. And the R squared of our estimate is kind of 0.9, which is fairly good. So then we are going to combine this information of what fraction of lines are underground with the fire probability map that's provided by CAL FIRE in their resource assessment program. So this is a publicly available data. So what we find is kind of interesting, so you can see here on the bottom, there is the in red, the wildfire probabilities across California. And then on the right-hand side is really we are kind of plotting the undergrounding rate for when the wildfire probabilities are high. So only conditioned on those locations where it's high. And you can see here, some conclusions is that here in California, regions the east of Central Valley have comparatively high wildfire risk, low income levels in the population, and very low undergrounding rates. So they're at very high risk of power outages due to wildfires if the actual fires happen. But if in regions on the eastern edge of the San Francisco Bay Area, that's like places like Livermore, Pleasanton, and so on, they have high income levels and high undergrounding rates. So we are started seeing this kind of heterogeneity or disparity, and we wanted to understand it a little better. And so, yeah, so Alejandro said I have 12 minutes left, and I'll wrap up in 7 minutes, Alejandro. So the undergrounding.
That was 5 minutes ago, Ram.
Okay, so sorry. So the undergrounding rates. So our conclusion is, first of all, the undergrounding rates correspond to the density of construction. That's how those decisions were made. Unfortunately, that also means that undergrounding strongly correlates with income. So, lower income people, even though they pay for undergrounding, they are not protected by it. And it's totally unrelated to wildfire probability distributions. And so we confirmed that with the regression. We designed an algorithm that kind of calculated how much it costs to bury the critical lines, because many of these feeders can have, more than one substation they connect to. And I'm going to skip that and just go to the end. So similar to what we did for these technologies, we were also able to kind of map EV chargers from building permits. And you can see here the NREL database, and this is kind of the EV chargers that we find. So this will enable a lot of interesting studies as well. And my conclusions here are just that, the atlas that we built is able to build these comprehensive resource maps in different locations in the globe. Overlaying the various layers reveals important technical, socioeconomic, political problems. And I wouldn't definitely discount this issue of disparity. We keep seeing it again and again in what's happening right now. New modalities of mapping are needed for storage systems. So we started working on that with a colleague in computer science. The idea there is that, you can use internet traffic data to try to detect some of that. We are also trying to figure out if you want to understand climate adaptation from a grid perspective and how DRs can support that, and how the most vulnerable populations are affected by it, how to do that analysis. So we're partnering with some colleagues here. So thank you very much.